So I'm sure there are many companies that operate successfully on pure microservice or pure monolith architectures, but many more of us exist somewhere in the middle. And in those in-between spaces, it can often be difficult to maintain and care for a business-critical legacy monolith when a lot of the energy and excitement of development has moved on to microservices. What I have for you today is a story about one such instance. My name is David Amin. I'm an SRE at Duolingo, and this is how we avoided Cachepocalypse. First things first, I'll walk you through our architecture and explain the bug that we were seeing. Then I'll tell you how we tried to go about solving it, how I inadvertently broke Spanish globally for about an hour while doing so, and then how we actually fixed everything, and some of the lessons that we learned along the way. At Duolingo, we run a large Python monolith. It's about 10 years old, and it's mostly in maintenance mode. There's not a lot of new code being added to it right now. There's a team that nominally owns the monolith, but they're not the ones that originally wrote most of the code. Most of our development these days happens on dozens of Java and Python microservices that interact with the monolith to fulfill our core user experiences. Unfortunately for us, there was a bug that had been lurking in the monolith almost since its beginning that was going to creep up. You see, Duolingo is a language learning app. This means that most of our data is what we call language data. This is how we generate exercises in a target language for a learner to do. Fortunately for us, that data is fairly easy to cache, so we make heavy use of a large memcached cluster. The monolith connects to every single node of that memcache cluster, and ordinarily we run about 2,000 monolith tasks, each with 16 processes, for a not insubstantial but healthy 32,000 connections per node. But wait, there's more. We started seeing duplicate connections to just the first node of the cache, which was very surprising to us. You can see what an outlier it was on this graph here. It was definitely much higher than the baseline, but we weren't quite sure why. The reason this was problematic for us is that during periods of peak traffic, we would be running over 64,000 connections to that first node, and that's very near the limit. And if we hit the limit, we can't scale further horizontally. We can't spin up new monolith tasks, which is problematic when we're trying to handle an ever-increasing amount of user traffic. So this is what we dubbed the Cachepocalypse. We knew this was a big problem. We'd actually been paged about it a few times, but it hadn't gotten addressed because the ownership was very unclear. The team that was being paged for it is the team that supports the memcached cluster, but it wasn't clear if it was their responsibility to fix it, or that of the team that owns the monolith but didn't write the cache code, or maybe the team that owns the language data itself. Because of this question, nothing was getting done. Fortunately for us, a few engineers were particularly motivated and noticed the problem, and so they put together a meeting with all of the relevant stakeholders. The first thing we did there was actually not talk about ownership, but about the stakes. People are understandably generally pretty reluctant to chase down a random bug in a poorly understood legacy code base, especially if it means deprioritizing other commitments that they've made to the business. But when it's clear that that very same business is on the line if we don't do anything, it becomes a much easier sell. Fortunately, once we had aligned on those stakes, people were willing to volunteer to start working on the problem, and we could begin to discuss solutions. We talked about potential solutions such as introducing a memcached proxy tier so that we could lower the number of overall connections, or reducing the resource usage of the monolith so that we could scale in a little bit and buy ourselves some time. But we estimated that we only had about 3 weeks to fix this at our current rate of growth, and those approaches had quite a few unknowns that we didn't imagine we'd be able to work through in time. One approach that we thought of that was well understood was to spin up an entire secondary memcache cluster and have half of our monolith nodes connect to that. This would have bought us a lot of breathing room, and we didn't anticipate any cache coherence problems or anything like that. The only thing we didn't love is that it would double our Elasticache costs. All the same, we decided to task one team with pursuing that approach, while another team worked on fixing what we were pretty sure was just a bug in the monolith. I joined the team that was doing the debugging, but unfortunately, there wasn't a great place to start. None of us were experts in the monolith, so we just started out with a cursory read of the code and theorizing about where the problem could be coming from. From our first look, we suspected that maybe it had something to do with how we were doing auto-discovery to the Elasticache nodes. Unfortunately, that meant that the problem would only be visible in staging or in prod. Because of this, and because over the years, the local dev story for the monolith had actually deteriorated quite a bit, we decided to start our testing in staging, which had a few important consequences. Most noticeably, it made our iterations very slow. We had to do a deploy anytime we wanted to test a theory, and then run some extra code to trigger the bug, which added up to about 15 minutes. That might not sound like a lot, but when you're testing dozens of different theories in a given day, it really does add up. The other issue was one of observability. We didn't have a good way to see inside the app to understand what was going wrong. We had a couple of metrics for connection counts, but other than that, we just kind of had to fall back to print line debugging. And so we entered into a cycle of reading bits of code, theorizing about where the problem could be coming from, adding log statements, but it was really slow and we weren't getting anywhere. Time was of the essence, so we tried a few Hail Mary solutions. We upgraded the third-party cache library that our monolith uses to connect to memcached, hoping that maybe there was some bug fix there that would help us out. We proactively closed a few connections we know would never be used to try to buy back some space, but we weren't really getting anywhere with those approaches. Ultimately, we decided that the only option left to us was to remove all cache code from the monolith entirely in stage, let the connection counts drop to 0, and then slowly reintroduce it to narrow down the source of the issue. This actually worked out fairly well. We found one particular module that when we reintroduced the cache code, we were able to reliably reproduce the duplicate cache connections issue. I gave it a much closer look and found a particular nested read in that module that was unlike anything else we did in the monolith. I thought that maybe in some way this was contributing to our problem and decided to rule it out as a variable. So I took the cache read out and deployed to staging. Unfortunately, this is where disaster struck. Unlike all the things that we had tested before, when I deployed this change to stage, suddenly the prod monolith started throwing hundreds of thousands of exceptions of the form that you see here. This was extremely confusing. This was like spooky action at a distance. I had deployed to stage was still working, but suddenly prod couldn't read our data, and it thought that our text strings were long values. This made no sense. But nevertheless, we began our incident response. I joined the war room, and I knew that the timing couldn't be a coincidence. Thankfully, at Duolingo, we run a blameless culture, so I had no reservations about bringing up the fact that it was almost certainly my change that had caused this outage. It was at this moment that I learned that apparently our stage environment shares a cache with our underlying prod environment, and a few other engineers couldn't quite see why my change had caused this, but we theorized that something I had done had subtly corrupted the cache data. This was further confirmed when we realized that the only language impacted was Spanish, which is the language I'm learning. We decided our best available course of action would be to flush the cache nodes, but we had to go one at a time to avoid overwhelming our origin and causing undue impact on learners that were not currently affected. This took about 45 minutes and was, as I'm sure you can imagine, quite stressful. But at the end, we were able to see signs of recovery and get back to a working state. Now, breaking prod never feels good, but what really annoyed me about this was I didn't understand the outage. We didn't really know why the data was corrupted. I decided to extract the module that we knew was problematic from the monolith and start running it in local dev against memcached. You can imagine this being a line of the entry in the cache. The data looks fine. I couldn't reproduce the error no matter what I did, but a colleague linked me to a GitHub issue that shed some light on the situation. I didn't know this, but it turns out in memcached you can store arbitrary metadata with all of your values. And the library that we were using uses these as bit flags to indicate the type of the data being stored. We had upgraded that library in staging, but not in prod. What we had missed was that there was a non-backwards compatible change in between the versions that we jumped. So when I removed the cache read from staging, the monolith helpfully wrote back into the cache with a flag set indicating that the data was Unicode. Unfortunately, the same version in prod indicates that that same flag means Boolean data. Booleans in Python are numbers, which is how we got to the long parsing error from before. This was good. It meant that we understood our outage, and we could have a very interesting postmortem and make changes to prevent a repeat of this exact incident in the future. But this did very little to help us solve the underlying duplicate cache connections issue, and time was still ticking. But I had an idea. I now had a reasonably high-fidelity lab environment in local dev, so I spun up a memcached cluster in Docker and tried to reproduce the duplicate connections issue. I was able to do so, but fortunately this time, it was really easy to iterate, and I had tools available to me to understand what the app was doing, like a local debugger. I stepped through and was able to find out that in the module that was affected, in a way that we had not expected, setting configuration options on the cache connections after they were initialized left a lingering connection to the first node. This was surprising to us, but it did mean that I could put together a relatively quick fix by just passing those same options in the constructor. It didn't have that behavior. I didn't really have to change any business logic, and so I deployed my change to staging, this time on an isolated cache cluster to prevent a repeat prod outage. And it worked. We did careful code review, and a couple of people worked with me to put together a plan to gradually roll this out to prod to ensure that we would minimize any potential damage if there were unexpected variables. And you can see the results of that effort here. The outlier node 001 converges to our baseline as we do the gradual rollout, which is exactly the behavior we were looking for. This was awesome. This meant that we had taken a problem with complex technical details, unclear ownership, an urgent deadline, and severe business impact, and we had solved it. Some of the factors that were important in our success here were making space for people to volunteer. We weren't getting anywhere talking about the ownership conversation, so we switched tact and started talking about stakes. It was amazing to me the people that were willing to step up when we understood what was on the line. The other important piece was making it safe to take risks. When you're working with a poorly understood legacy code base, things are unlikely to go exactly the way that you plan, and you need to make it safe for things to go wrong. For us at Duolingo, that looks like running a blameless culture so that we have psychological safety when things do go wrong, but also having a backup plan in case our preferred approach failed. The thing that I wish we'd done earlier was to invest in fast and safe debugging. This was ultimately the thing that made the difference in being able to figure out where the error was, and if we had invested in our local dev story a little bit sooner, we probably could have avoided a prod outage. All the same, within just a few weeks of deploying this change, we had scaled beyond the point we otherwise would have been bottlenecked, which proved the importance of our urgent response. Excuse me. Thankfully, in the months following that change, we were able to make longer-term improvements to ensure that this cache connections problem would not become a bottleneck for us in the future, and we could continue providing the best possible quality of service for our learners going forward. And that's all I got. Thank you.